I'm going to go ahead and set the stage. So just like before, we've done a problem similar to this. We're looking for a different thing. We're factoring and finding when the height of like a ball thrown off the top of a building when its height equals 0. We're given a height function and all this. Now imagine, once again, similar setup. We have a building that's 48 feet high. And somebody's throwing a ball off of the top down to the ground. So from here, from a building, a ball is thrown straight up with an initial velocity of 32 feet per second. And here is the height function. Just like before, we're actually just given this one, h of t equals negative 16t squared plus 32t plus 48. Of course, this gives the height wherever the height is at t seconds. So give me, if you plug in seconds, you get out the height. So for example, at time equals 0, when we've first initially just thrown it, we're at 48 feet high because the building's 48 feet, and that's where the ball is starting from. Okay, now the question is this. Find the maximum height of the ball. Max height of ball. Now, notice that a couple things. Function given to you is a parabola. You don't necessarily need to like graph it or anything to figure out what's happening. Here is the parabola, at least part of it. Technically, there's like a little invisible part. Looks like that, but we're just focused on throwing from here all the way down. Now, it wants to know the maximum height of the ball, and the maximum height is that spot right up here, right before it starts going down. Actually, I'm going to make it go right here, right before it starts going down. So this is the point of max height. Okay, so notice this is something we know. When we're looking for the maximum of a downward facing parabola, or alternatively, like the minimum of an upward facing parabola, we're just looking for the vertex. That's it. We're just looking for the vertex of this. So, remember, side note, vertex looks a lot like this. Vertex is a point, just like this is a point on this parabola, and the coordinates are the x value is negative b over 2a, and to find the y value associated with that, you just plug that x value into the function. That's all. So, in this example, let's find it. So, here's our A, here's our B. We actually don't even care about C in this case. So negative B, which is 32, over 2 times A, which is negative 16. So we have negative 32 on top, 2 times negative 16, negative 32 on bottom, which gives us positive 1. Now, just like with other word problems in general, if you're thinking about physically what's going on, sometimes you can catch yourself in an answer to see if you've made a mistake or not. So what I mean by that is, in this case, our x and y values for this problems are actually t and h. So we're really dealing with like t-axis versus an h-axis. X versus x and y doesn't really matter. It's really the same thing, but now we have actually concepts to put to these axes. Is here's our time is our x, and our h is our y, our height. So what we found here was an x value, in this case a time value. And so we got a time value of 1 second. So let's say you dropped like that negative and you ended up with like negative 1 seconds. Well, negative 1 seconds in the context of this problem just means we're going backwards in time, which typically doesn't make any sense. So in word problem stuff, sometimes you can double check yourself to see if something is actually physically possible. So what this is, though, is this is giving us a t value. Now the question is, find the max height of the ball. Now, if the question was, when does the ball achieve its maximum height? Here it is, 1 second. After 1 second has passed after throwing. So now we still need to find the y value for this guy. So all we need to do is take t equals 1, plug it into this height function. So if we plug a time into this guy, it spits out a height. So it's height time. So we're just going to plug in 1, so we get negative 16, 1 squared, plus 32 times 1 plus 48. Okay. So negative 16 plus 32 plus 48. 32 minus 16 is 16 plus 48. Well, 6 plus 48 is 54, plus another 10 is 64. So our vertex in the context of this problem was 1, 64, meaning the vertex was after 1 second. We're at 64 feet in the air, and since this is the vertex of our height parabola, after 1 second is when we achieve a maximum height of 64. And then 64 is your answer. That is the maximum height of the ball. How awesome is that? All right, cool. So let that sink in. I'll just keep this up here for just a second. Actually, I'll erase the top part of this. I know you guys won't mind too much, and it is kind of against the style of the class, but I'm just going to go ahead and do these examples. I have 2 more of these. Typically have you guys try them on your own, and I'd come around and talk to y'all, but times have changed. If a person asking if not exactly review, finding the vertex, I guess, is something we went over because we were graphing quadratic equations, but the concept of word problems and finding the maximum of a quadratic, that part of it's a new concept. So this is effectively a new concept, but we're using the vertex, which is something we did go over. A long story short, I mean, vertex is the very tip of a parabola up or down, and this is how you get it. Of course, the b and the a coming from the coefficients of the quadratic equation. Okay. Is everybody satisfied with this one? Okay. All right. Here's the deal, folks. Stick with me for a bit today, and maybe we'll wrap this one early today, since we are quite a bit ahead of schedule. Because even if I wrap this up early, tomorrow we're going to go over new stuff, leaving quadratics for the time being, and we'll still be a little bit ahead of schedule. Okay. So, if you guys are satisfied with this, here is example 2. Let's say you have, it says a farmer has, let's say you have 1,000 feet of fencing. And you want to build a rectangular enclosure. So not a square, not a trapezoid, but you want to build a rectangular enclosure, whatever. With a river on one side. So basically what that means is you're going to build, you have 1,000 feet to make this fence right here, but you don't need fence on this one side because that's just river. So these 3 sides will be made of fencing. Okay. Now, with this setup in mind, we want to know to maximize the area. What should the dimensions be? What should the dimensions be? Okay. So once again, if you see something like maximize this, minimize this, what have you, we know that we're going to be building up to a quadratic equation of some sort. And then we're going to find the vertex and then find the y value associated with the vertex. So first things first is we need to figure out an equation. Now, in this case, we have a rectangle. So we know that these sides will be the same. And this side will be its own thing. Its mirror, its buddy is this river. So I don't know what these little sides are, so I'm going to call those both x and this side y. Now, we have 1,000 feet of fencing. So we don't have exactly perimeter because we have one side that's all river. So we know that 2x plus y is going to equal 1,000. And this is like sort of y. Okay. Okay. So we have this information right here. 2x plus y equals 1,000. But what we want to maximize is the area. But the area inside area is what we care about. This is what we want to maximize. But our area looks like this. Area of the rectangle equals, of course, x times y. Even though one side is just the water, we can still think about the length of these sides, and that's how we're going to grab the area, x times y. Now, we don't know the area, and at this point, it actually doesn't really matter. We just want it to be maximized. So not knowing the value is okay here. Now we sort of have this, without this number, this is going to look a little weird that we don't have this number here, but we do have a system of equations here. We have x and y related to each other in two different equations. So, not really looking like a whole lot of room to eliminate, so let us go ahead and solve for y here, which is y equals 1,000 minus 2x if we subtract 2x from both sides. So now our area is going to look like x times y, but y is 1,000 minus 2x. Simplifying into 1,000x minus 2x squared. Now, rewriting this slightly, so our area equation looks like this. And I'm just doing it in this order just for standard, familiar look. Oop, that's 1,000. But we have a quadratic. Here's our A. Here's our B. Once again, we're trying to maximize area. Have our area all out in one variable. Let's figure out the vertex. So in this case, vertex live, we're looking at negative b, which is 1,000, over 2 times a, which is negative 2. So this is negative 1,000 divided by negative 4, which gives us a positive 250. I just thought about how many times 4 goes into 100, and then added a 0 on that. So that's our x value. Since that was our negative b over 2a. That was our 250. But once again, we're just looking for the dimensions here. We're not necessarily looking for what the maximum area is. If we wanted to, we would plug this 250 in here. But for one, I'd have to square 250 and it would just get a little weird. But we're not asking for the area. We're asking to maximize the area, what should the dimensions be? So we just care about the dimensions. So we have our x, that needs to be 250. Yeah. And we already have a relationship between x and y. So, oh yeah, I'm going to erase this stuff. So we know that x is 250. We also have that y equals 1,000 minus 2 times x. But if x is 250, then we have that y equals 1,000 minus twice 250, which is 500. And 1,000 minus 500 is 500. This is how we defined our x and our y right here. This length is 250, this is 500. So the dimensions and the answer is that this thing needs to be 250 by 500. I don't know what it was. Yeah. Cool. I'll go back over this in just a sec. Just like a little overview, piece by piece. So set up 1,000 feet of fence, building an enclosure across a river, meaning we don't need to care about this side of the fence. Now, we do need to care about these 3 sides, so those are going to be fenced. So it's rectangular, so this side and this side is the same. And we need to know kind of like the perimeter of just the 3 sides. So that is 2x plus y equals, that's just 1,000 feet of fence, which we could simplify solving for y. Now we don't have an area. In fact, we're trying to maximize area. So when it's asking you to maximize the area, that means you're going to need to find the equation of area. Whether or not you have all the pieces, you need to just at least set up what the area looks like. So our area of this rectangle, is, of course, is going to still just be x times y, just as it always has been. But we can replace this y with stuff in terms of x. So our area equals this negative 2x squared plus 1,000x, whatever x is. But as you see, this is a problem. It's still quadratic. So we can still look at the vertex. We can still maximize this thing. Of course, anytime we're looking for maximizing, we have the appropriate equation. We have the quadratic. We're just going to find the vertex. Negative b over 2a. That's it. And that's the x value that we needed. gives us 250. We have the relationship between x and y already. That's what we needed. We needed the dimensions. Feeling all right? Questions, comments, anything? All right, y'all. Strap in. One more thing we're going to do. And when I say one more thing we're going to do, I think I mean it. Hold on, I'm about to sneeze. Got it. All right. All right, no more questions. Here we go. Okay. Yes. So in this case, here is our area function, right? So we found the x value for this, for maximizing this. And if we were to take this x value, and if we were to plug it into here, it would give us the maximum area. But the question wasn't asking for what is the maximum area, it just wanted to know the dimensions. So you could have done this, and you could have been fine. Notice that I have labeled this differently as not y. This is like a sub r, or area of the rectangle. And y is still over here somewhere. A little bit, it's separate from this. In fact, it's in the equation for the area of the rectangle. So we could easily take this 250, put it in here, and that would give us the maximum area. But we just wanted the dimensions. So yeah, totally correct. Okay. I'm going to go right along here into the third and final example. Okay. Let's say there's a machine you have, and it costs to run this machine every minute. So we are on now example 3. The cost to run a machine by minutes, we're going by minutes. So a cost per minute situation is this function. So our cost function in terms of minutes, so we're going to plug in minutes, we're going to get out cost, looks a little bit like this. 2.2 m squared minus 66 m plus, good heavens, 655. I didn't come up with this problem, not gonna lie to you. This is a lot of crazy numbers here. And there's like a decimal, like, anyways. So, question is this. So here's our cost function. question is this. For what number of minutes is the cost, of course, the cost of running the machine, a minimum? Hey, look at this. Now we're actually doing minimum stuff. Because notice, minimum. Notice this is an upward facing parabola, unlike our last two. So it looks like that. So basically, as time moves on, it starts off real high at early time, eventually gets real low, and then it gets costly again. Of course, we're looking for this guy, our vertex. Now the question is, for what number of minutes is the cost a minimum? So therefore, we're looking for, thus the question is, what is n? And then we're going to also look for the minimum cost. What is this fantastical minimum cost? Of course, now what we're looking for is C of n, or y. Okay. C of n. Okay. Now, really, here's the idea with these word problems. If you know what you're doing, then we're basically on our way to being done. Because if here's our function, want to find the minimum minutes, just take the function we're given. Here's our A. Here's our B. So if we already know that we need to find the vertex, if we're maxing or minning something, we can just dig right in. So negative B. B in this case is negative 66, so negative a negative 66 all over 2 times A, 2.2. Fortunately, we don't have to actually use the 655 what up. So negative 66 is 66. 2 times 2.2 is, as you might imagine, 4.4. Of course, now we have to figure out this nonsense. Now, of course, you won't be given decimals, but maybe you will now because technically you have access to calculators through Alex. However, just as a little extra for you guys showing up today, I'll show you a little magic with decimals. So we're looking at 4.4, right? So 0.4, if you guys remember decimals, this is complete sidebar, by the way. This is just me turning this into a fraction and my thought process. This is the 10th place, right? So when you do decimals, you have the 10th place, 100th place, 1000th place, yada, yada, yada. So this is the 10th place. So that means we have 4 tenths. That means we're dealing with 4 and 4 tenths. Pretty rad. But of course, we can reduce these fractions. So what we're really doing is 4 and 2/5. Not even sure I want to do this, so I'm going to keep going. So of course, now we have this mixed number. And as some of you may remember, to get to the improper fraction, you're going to multiply the denominator together. And then you're going to add whatever that is to 2. And put that all over 5. So 5 times 4 is 20, plus 2 gives us 22 over 5. which means 5 goes into 22 4 times with the remainder of 2. So we're back here. So this is actually 22/5. Now, that's all well and good, but how does that help us? Well, that means that we actually have 66 divided by 4.4. We just decided that 4.4 is 22/5. So 22 over 5. But we know how fractions work. We don't want to divide. We're going to multiply by the reciprocal. This 22 goes into 66 3 lovely times. And we're left with 3 times 5, which equals 15. Which answers our first question. This is the number of minutes that the cost is a minimum. And all we need to do was do some vertex action. That's it. Now, this is where it gets slightly magic indeed. This is where it gets slightly ridiculous. In this specific problem, and I'm glad I'm doing this one by hand, because now we need to plug 15 into this nonsense. Good heavens. Now, bear with me for a moment. For those of you that are actually sitting there in front of your screen watching this, 2.2 is 20, what did I say, it's 22/5? Nope, that was 4.4. That was 4.4 is 22/5. But I just want to take half of 4.4 to get back here, 2.2. So I'm going to take half of 22/5, which of course is just 11/5. The reason I'm doing that is we're going to plug a 15 into this craziness. So we have 11/5, boom, times 15 squared minus 66 times 15 plus, good heavens, 655. Okay. Well, here we go. I'm going to try to do some heavy math in my head. So we have 11 over 5. I'm going to do this like this. So this is 15 squared, which is 15 times 15. So this 5 cancels with one of these to give me a 3. Which doesn't help too much. This is just this first part. Because now what we have is like 11 times 45. See, 11 times 45 is the same thing as, this is fun, 10 times 45 plus 1 times 45. So this is 450 plus 45, which of course is 495. I'm not gonna lie to you all, I'm not sure why these numbers are so large, but if you bear with me, y'all can leave in just a moment. Okay, so this first thing is 495. Then we have 66 times 15, and I'm not even gonna. It's calculator time, y'all. Which is 990. So 495 plus 655 minus this big guy, which is 990. Okay. Now, $495 plus $655, $1150. minus 990. When we subtract this 990, we get 160. Now, all of that work just to finally give us what the cost was going to be. I might have been easier to simplify this stuff, but long story short, given a cost function that happens to be an upward facing parabola, thus, if it's upward facing, we can find a minimum. Looked at the vertex, negative b over 2a, breaks down into 15. Since this was cost versus m, we have m minutes, m being our input or our x versus our cost. So this is our m value slash x value, if you want to look at it that way. Thus, we found that to get the minimum cost, the minutes we have to run this thing is 15 minutes. And then we just did this bunch of gobbledygook right here to plug 15 in after we did all that algebra. We ended up with 160 minutes. So 15 minutes was the timing, and of course the minimum cost is 160. And there she blows. Hey, actually took up the whole time. What do you know? All right. Well, if you have no more questions, you're free to go. If you have any questions or concerns or comments, please let me know.